Hello everyone, I am MD Siddiqur Rahman and the co-authors are Lohan Lapase and Zozian Moth. I am going to be talking about aircraft conflict resolution using convolutional neural network on trajectory image. So before going into detail, let's see what the conflict situation look like. Simply, a conflict situation is that when two or more airplanes find themselves less than a minimum distance apart on their trajectory. It is called a conflict situation. In this case, the minimum distance between two aircrafts is 5 nautical miles horizontally. To resolve a conflict, the basic parameters that a controller considers are the position, speed of the involved aircrafts, weather, flight plan, destination, and many other parameters. By considering those parameters, the air traffic controller can take a decision to modify the initial flight plan of any aircraft. Let's see a little more clearly. To resolve a conflict situation, the air traffic controller think of those positioning information and decide on actions pilot have to apply on the fly. There are different types of conflict, but in this study we consider only the horizontal conflict at en route level. Also there are three types of conflict in terms of distance: short range, mid range and long range. In this study we consider the mid range conflict only. At this en route level, typically aircraft heading changes are applied to resolve the conflict. These changes can be in different ranges of heading degree to the right or the left. In our case, we fix it from left 30 degree to right 30 degree by 5 degree. So to resolve the conflict, air traffic controller consider all the positioning parameters such as latitude, longitude, altitude, speed, headings of each aircraft involved in the conflict, then take a decision to change the heading of one or more aircrafts. Many research works have been proposed on aircraft conflict detection and resolution. Although most of the initial research in conflict detection and resolution was based on mathematics. According to Farm, it is essential for these models that the information is noise-free since the aircraft positions are approximate. However, recently research moves to the machine learning. Many machine learning methods are proposed in which all the flights are assumed to be allowed for free routing or free flight. So the planes share their information from the onboard system. In this case, the pilots of all the aircrafts involved in the conflict can resolve the conflict by communicating within themselves without the help of air traffic controller. An ensemble approach was applied for conflict detection in free flight by data mining in 2009. Also, the linear models and the SBM model are applied in free flight for conflict detection and resolution. Although it is interesting, in reality, its application is still a long way off because free flight is not yet in practice. Since annotated air traffic control data is difficult to obtain, many methods have been proposed based on reinforcement learning to resolve aircraft collision. Beaton and Wee applied two-level deep reinforcement learning in a hierarchical way, while Pham in 2019 proposed a single agent-based deep reinforcement learning for two aircraft at the same altitude. Zhao and Liu in 2021 also applied reinforcement learning and convolutional neural network using image data where each image contained the current position of aircraft associated with the conflict. However, a proper reward function is required for the best resolution of reinforcement learning, and finding that function is the most challenging task because it depends on features like certain rules and conditions. There are very few supervised learning applications for aircraft collision detection and resolution. Kim proposed two different supervised models, one based on neural network, the other based on multiple support vector machines. Both are based on multi-class classification, where the best output is selected based on the highest probability score. A multi-level classification of aircraft heading changes using neural network was proposed to resolve the conflict. It is similar to Kim's model but for multi-level classification. In this case, multiple alternative solutions are possible for a single conflict. In this case, author used simulated data. The advantage of using simulated data are that many variations are possible with simulation data that may not be obtained from actual data. Also, they used last 5 minutes of trajectories, which is a series of location of all the aircraft associated with the conflict. This model only solved the horizontal conflict at the en route level. The main remaining challenge is that there is no supervised learning method that can handle a variable number of aircraft. In our research, we combined the idea of these three concepts. So in this research, the initial trajectory data was the same as that used for the CRMLNet model. The problem with the current supervised model is that the input parameters depend on the number of aircraft. Since the input number of a machine learning model cannot be changed in real time, it is a big challenge for an undefined number of aircraft. To resolve this problem, we converted the trajectory data into images considering the 5 minute of trajectory. This research aimed to provide a generalized model to resolve a conflict where a variable number of aircraft are involved. Two things were considered. First, create image data from trajectory sequence. Second, find a convolutional neural network based model to classify these images. We define a relatively small convolutional neural network based model. We call it ACRNet. Therefore, our objectives are convert 5 minute trajectory scenario into image data. Then the image size will be the same even the number of aircrafts is changed. Therefore, we can handle a variable number of planes without changing the model architecture. Also, not only can conflict be resolved between aircraft, but also between aircraft and other spaces such as weather, military zones, etc. Finally, we show the comparison between trajectory-based CRMLNet model and image-based our ACRNet model. So, as we have discussed before, to combine ideas of using 5 minutes of trajectory into image data and multi-level classification, here we combinedly propose a model of aircraft conflict resolution based on convolutional neural network. We named it ACRNet. We trained and tested our model where each image contains aircraft conflict scenario and the output class labels are all the heading directions from left 30 degree to right 30 degree, that is 12 headings. Then we compared our ACRNet model with CRMLNet model while the output class labels are same for both models. But the input of ACRNet is image while the input of CRMLNet is trajectory data. Let's see some results to compare them. We compare our ACRNet model with the CRMLNet model using tenfold cross-validation, where the input data of ACRNet are image and of CRMLNet are trajectory sequence. We also compare ACRNet with two other widely used convolutional neural network based models, that is VGG16 and ResNet. Table 1, Block 1, we use two different data for ACRNet, where ACRNet2 used the image containing two aircrafts, while the ACRNet3 used the image containing both 2 and 3 aircrafts. Block 1 and Block 2 show the accuracy of ACRNet and CRMLNet that ACRNet perform better than CRMLNet in the case of two aircrafts, while Block 3 shows the score of VGC16 and ResNet. They do not perform well compared to ACRNet. This may be due to their many layers. If there were more samples, the performance of those models may be better. The main purpose of our research was not to find the best image processing model, but to easily overcome the challenges of existing sequence-based models through image processing with higher performance. Now, if we look at the loss and accuracy curve, we see both ACRNet and CRMLNet performs almost similar, but CRMLNet looks a little bit better than ACRNet. Let's see one more results. These figures show the individual heading prediction score of each conflict. Here x-axis of both A and B presents the total number of heading decisions and the y-axis is the probability between 0% and 100%. All the dots above the green line in the middle are the positive class and below are the negative class. All red dots are incorrectly classified that are bounded by the blue lines, while green dots are correctly classified. The distance between blue lines, that is incorrectly classified boundaries, is shorter for ACRNet than it is for CRMLNet. The blue lines are overlapping on the 0% and 100% score line for CRMLNet. It means there are some incorrectly classified samples that are close to 0% and 100%. Thus, ACRNet is more confident than CRMLNet because the shorter the distance between the blue lines, the more confident the model is. So, overall ACRNet performs much better than other models. In conclusion, this research aims to provide a generalized model to resolve a conflict where a variable number of aircraft are involved. An interesting aspect of using image data is that it can be used not only for conflict between planes but can also contain other information without changing the image size, such as weather, thunderstorm, military zones, etc. Our future research will include that information for better resolution of aircraft conflict as well as more than 3 aircraft. Finally, I would like to thank to the conference for accepting our paper and also the institutes to support me financially. Thank you very much.